The universe is filled with mysteries. Black holes warp space and time. Galaxies collide in spectacular displays of energy. But there is one mystery, closer to home, that rivals the cosmos in its complexity and wonder. This is the mystery of intelligence. How does the human brain, a 3-pound universe of neurons, give rise to thought, creativity, and consciousness? For centuries, this question remained in the realm of philosophers and theologians. Then, in the mid-20th century, a new field of science emerged, one that dared to dream of creating artificial intelligence. This was not just about building machines that could calculate or follow instructions. This was about building machines that could think. The quest for artificial intelligence, or AI, is a journey into the unknown. It is a journey that has already led to incredible breakthroughs, transforming our world in countless ways. AI is now used in everything from self-driving cars to medical diagnosis, from personalized recommendations to fighting climate change. And yet, we are only at the beginning of this incredible journey. The future of AI holds both immense promise and potential peril. To navigate this future wisely, we must understand the origins of AI, its evolution, and the ethical challenges it poses. Join me now as we explore the incredible journey of AI, from concept to reality. The story of AI begins not in a laboratory but in the mind of a visionary mathematician. Alan Turing, a British codebreaker and computer scientist, is widely considered to be the father of theoretical computer science and artificial intelligence. In 1950, Turing published a groundbreaking paper titled Computing Machinery and Intelligence. In this paper, Turing posed a simple yet profound question: can machines think? At a time when computers were little more than glorified calculators, Turing's question seemed like something out of science fiction. But Turing was not interested in building machines that could mimic human behavior. He was interested in something far more fundamental: understanding the nature of intelligence itself. To answer his own question, Turing proposed a test, now known as the Turing test. In this test, a human evaluator interacts with both a human and a machine, without knowing which is which. If the evaluator cannot reliably distinguish the machine from the human, then the machine, according to Turing, can be said to be thinking. The Turing test has been both influential and controversial. It has sparked countless debates about the nature of intelligence, consciousness, and what it means to be human. While no machine has yet definitively passed the Turing test, it remains a benchmark in the field of AI, a reminder of the audacious goal of creating machines that can truly think. The early years of AI research were marked by a sense of optimism and ambition. Researchers believed that the key to creating artificial intelligence lay in symbolic reasoning. This approach, also known as good old-fashioned AI or GOF-AI, was based on the idea that human thought could be represented by symbols and manipulated according to rules. One of the earliest examples of symbolic AI was the logic theorist, a program developed by Alan Newell, Cliff Shaw, and Herbert Simon in 1955. The logic theorist was designed to prove mathematical theorems using symbolic logic. It was a remarkable achievement for its time, demonstrating that computers could be used to perform complex reasoning tasks. Another notable example of symbolic AI was Shardlu, a program developed by Terry Winograd at MIT in the late 1960s. Shardlu was a virtual robot that could understand and respond to natural language commands. Users could instruct Shardlu to move objects around in a simulated world, ask it questions about the state of the world, and even have it reason about its own actions. Section 4. Expert Systems, Early AI Pioneers. While symbolic AI showed promise in limited domains, it struggled to scale up to real-world problems. The real world is messy and unpredictable, full of ambiguities and exceptions that are difficult to capture in rules. To address these limitations, a new approach to AI emerged in the 1970s: expert systems. Expert systems were designed to capture the knowledge of human experts in specific domains, such as medical diagnosis or financial analysis. These systems used a knowledge base of facts and rules to reason about problems and provide expert-level advice. Unlike earlier AI systems, expert systems could explain their reasoning, making them more transparent and trustworthy. One of the most famous expert systems was Mycin, developed at Stanford University in the 1970s. Mycin was designed to diagnose and recommend treatment for bacterial infections. It was tested against a panel of human experts and found to be highly accurate, even outperforming some of the doctors. Expert systems represented a significant step forward for AI. They demonstrated the practical value of AI in solving real-world problems. However, they also had their limitations. Building and maintaining expert systems was time-consuming and expensive, requiring extensive knowledge engineering. Moreover, expert systems were brittle, struggling to adapt to new situations or learn from new data. Section 5. The Machine Learning Revolution. In the late 1980s and early 1990s, a new paradigm began to emerge in AI research machine learning. Unlike symbolic AI, which relied on explicit rules, machine learning allowed computers to learn from data without being explicitly programmed. This shift in approach was driven by the growing availability of data and the limitations of rule-based systems. Machine learning algorithms are trained on large data sets, identifying patterns and relationships in the data. Once trained, these algorithms can then make predictions or decisions on new, unseen data. There are many different types of machine learning algorithms, each with its own strengths and weaknesses. One of the most widely used machine learning algorithms is the artificial neural network, or ANN. ANNs are inspired by the structure of the human brain, consisting of interconnected nodes that process and transmit information. ANNs have proven to be particularly effective in tasks such as image recognition, natural language processing, and machine translation. Section 6. Deep Learning Unveiling New Horizons. In the 2010s, a subfield of machine learning known as deep learning emerged as a powerful force in AI. Deep learning algorithms are based on artificial neural networks with many layers, allowing them to learn complex representations of data. This depth of learning enables deep learning models to achieve state-of-the-art performance on a wide range of tasks. The rise of deep learning has been fueled by several factors, including the availability of massive datasets, the development of powerful computing hardware, and advances in algorithm design. Deep learning has revolutionized fields such as computer vision, natural language processing, and robotics. One of the most striking examples of deep learning is the ImageNet challenge. The ImageNet dataset contains millions of images labeled with thousands of categories. In 2012, a deep learning model called AlexNet achieved a significant breakthrough on the ImageNet challenge, achieving an error rate far lower than any previous method. This breakthrough marked the beginning of the deep learning revolution.